fields, which is unreal. And I think that is, I find it unusual. I think you could ask him questions from any perspective, and I always ask him dumb questions and he gives me very intelligent answers. It's nice, so I encourage you to ask him anything. Maybe one slide I'd love you to go back to is the 4 areas of, or the 4 problem sets that you identify. Way back with the Maxwell.
This is the beginning. Talking.
Upper right. No, you just had it.
This one?
Top right.
This one?
Yeah. So left one. So essentially, you're recognizing you can alter every one of those areas.
I'm saying that based on what physics knows today, that light is at the core of every one of those equations. So if you're doing something with light, you're changing out connectors, you're going to change the implications of every one of those equations. Every one. And that, in an arrogant point of view, that's the sum of what we know from a technology perspective. Right? That's really it. You know? Relativity, quant, and thermo and electromagnetism.
So I think questions can be asked of the conceptual nature or the practical nature. I think he was obviously touching on the potentials looking forward for application. So the first thing, you have a theory and it all the way through the production. You're kind of halfway there.
Yes, that's the thought.
Heading to, so
maybe closer to halfway for some.
I invite questions in as stammering as they may be.
So the question I have, which I thought about last night as I was reading through the applications, you seem to have 2 procedures that you tailor the material with, the photonic and then the thermal, the hot metal.
That's right.
And the photonic procedure, it seems like what you're doing is you're taking an ingot at room temperature, exposing it to different prescriptions of light, and that tailors the material.
Yeah.
Okay. Sorry, I'm looking through this.
I've had to work through it.
Why?
And you're doing a lot faster than me.
I just read it. But this.
That's why you're here, and I'm not.
This photonic procedure. Why does this not happen in nature? I understand that you're very specific with the light that you're supplying to this room temperature material, but it seems like the relation, the entire order of what we think is the universe got shifted for me last night, or what I think is the universe, because I'm wondering, if we suppose that matter and light are the same, but then the relations between them are infinite, why doesn't copper grow in nature? Why doesn't it?
That's a great question. And I'll try to give you an opinion.
Okay.
All right? I'm going to give you 2 things. I'm going to go. I'm going to take your first question, which is hot versus cold. All right? And my hot versus cold, one of the things that I've found is that in theory, I should be able to do the same thing cold as I can hot. Right? In theory. Or almost the same thing. But in practice, I can't. Right? And the reason is, or my opinion on what the reason is that on the natural copper, I'm sitting right here on a 2D surface, and it's got this structure, but I don't really know the structure. So it's like your symphony. I don't know if it's a jazz band back there, or if it's just a violin section. I don't know, right, what it is. And as I get the math better, and I get better opinions on it, I get better results. Having said that, if I take natural copper and I melt it, and I set it through a set of procedures where I think I know what the symphony is, I get way better results, right? And it's an ignorance versus other question. So why doesn't, so I have two procedures, right? I have the procedure for hot metal to make stuff, and then I have the room temperature light. And the obvious question is, why would you do both? And it's because I have people who are saying, well, how do you know it's a contaminant? Well, give me 12 nines pure silicon, I'll shine light on it, and I'll change the properties. Now you know it isn't a contaminant. So as soon as you're in a liquid metal system at 2,000-3,000 F, right, then you've got a variety of issues, and the bulk people will say, the condensed matter physicists will say, oh, there's so many different interactions, anything is possible. Prove it to me on a gas. Why don't we just do that, right? So, and that leads to a lot of different types of things, right? And when you get to contaminants, again, at room temperature with light, if I can move magnetism around pretty clear as a contaminant. So now let's go to the second question. Why doesn't copper grow, right? At least, why doesn't it grow like a tree, all right? I think that answer, this is a good question would be, could I make it grow like a tree? Well, that's an interesting question. A more interesting question. Here. That's easy way to do it. Okay. I have a very strong opinion on the periodic table. And one of the things that I found is plagued me my whole life. If you think of this as a card on a continuum, I know you all have it. I definitely do, right? And you move that along a continuum, it could be, hydrogen could start anywhere. And it could end anywhere over on this side. I mean, it's just one arrangement. But why there? Right? Einstein asked the question, you know, why, once you set all these symmetries in place, you have any variability in how you move things. Well, as I got into this, I started looking at what types of metals, what functionality was being used by biological systems. I've been trained well, some say. Well, what I've been able to do is I've been able to relate the connector character of certain elements to mathematical functions. So when I talk about coming down and then coming back out and then matching, there's this particular set of elements that if I want to bias the system, I want to put a cape on the system, I'm going to use that. And many times it will inform how I use the light. Right? So the issue then is, knowing that, I can then go to this slide right here. I can go to this slide. Comes down to here. Comes down to that equation. What's the accessibility of these functions in natural copper and room temperature? Now remember where natural copper came from, right? And the current belief is it came from the star, right? So it's vaporized, it's at the maximum entropic condition, maximum level of chaos when it comes to connectors, and it coalesces into a minimum energy state. We call it a geodesic, right? These systems are not immediately accessible in copper. Now flip it. Flip it to a carbon system. Much lower energy, much fewer shells in the system. So when you start looking at what the probabilities are that you can make a connection, way higher. I don't know if that's a good or bad explanation. I think to me, the issue is, could you grow copper?
So you're essentially saying, yes, you think copper can be structured sort of like carbon, just it didn't in the nanometer.
I think that, I think we're going to find, you know, one of the questions I have that I ask myself is, being married with 4 kids, right? It's amazing how resilient a kid is. Right? Amazing how resilient a kid is. And if you look at the human species and the environments that functional people, forget the emotional stability, right? Functional people sort of grow up in, right? Dirty water, crack houses, elitism. It's pretty amazing. It's a robust system in terms of making the various connections. So think about that robust system in terms of self-assembly, right? Is there a constraint? Is there a natural geometry that drives self-assembly? That's the constraint I'm looking at right now. And I think the answer is yes, right? So that when you know, one of the big things in medicine is they gave a Nobel Prize years ago for proteins. The proteins know how to fold, right? They have all the instructions set. Yeah, no doubt, right? You have all the instructions set to do a wide range of sports. But who tells you to do that sport? Normally the outside environment, right? So it's a combination of the cell, and I think that what we're seeing with stem cells and the like is really getting closer to these and triggering regrowth. Why is it that humans have 2 sets of teeth and a shark has infinite? Mice have 4 or 5. And the rate that they can be grown. I mean, do the mass energy balance around that. I have. Pretty interesting. Just go out and do it. Just go out and do it, right? Where did it come from?
So, I mean, 2 points. One, so I think he's unusual in thinking that this is at play in the biological world around us all the time. That's just what we've picked up on. Right? And you're sort of sensing that there's something very profound here about biological life. Maybe it's the key to life. It's a shift in property that just isn't well. The other one, last time we talked about waste and failure, Chris writes a paper for Nature magazine, and then they say these are big claims. This is a crazy stuff, man. Will you, we asked that you validate it. So Chris has to take his samples to various certified testing labs around the country. And kind of the letters that you've got framed of them sent writing back and saying, we're terribly sorry, but our equipment seems to be faulty. Because we can't identify this, or because the property is varying. And he's kind of like, yeah, that's what we're looking for. But they kind of refuse to be going to it. So, you know, it's that curious moment of demonstrating something which isn't within the canon of current understanding. And maybe is the key to understanding things like
But also put it in a form that's at least accessible. You know, one of my co-authors says, you know, this is a pretty wide stream. And if you want people to follow, you got the rocks in between. And one of the comments that came back from Nature was, you need to have more control experiments. Well, in a 4-page Nature paper, it's hard to put in the right control experiments. And we came up with a, big hop into it. Just real quick.
So maybe we'll do that everywhere around examples in Nature. It's very good. You get the thought, at least it's the potential of this to maybe produce things that don't occur in Nature. There's an explanation for that in the process of formation of matter as coming down from stars and it's come down to its particular energy level once you get an output, once you get a great novel property.
Right here. Took me a long time to figure out how to come up with one table that shows, I think if you did the math on it, about 200 control experiments. Right? Not one, not none. 200, right? Because let's be no mistake, I don't want to be wrong anymore, and the rest of us here, right? So how do you, particularly in a domain that you don't know anything about, how do you convince yourself that your reality is not a dream? Right? That's a, NASA has some very good techniques on that. Some very good techniques. And they're hard. They're hard to do because you have to get to the same solution with 3 different independent ways without any common mode failure. That puts a big burden on the person trying to do the problem. Right? It's like calling a meeting versus calling a meeting and knowing what you want on a meeting. Puts a lot of work up front, right? And getting one piece of, yeah, these are what we've done. These are all the different thermocouples, these are different lances, this and this. Non-trivial. But has nothing to do with science. It has to do with social engineering and communication. This is the one I was going to show you. It's right here. Dynamic property sets. Really the definition that a computer scientist would use, but what nature has taught us, right? So you've got the mantis, and it can change and adapt its colorings, these sorts of things, right? Over very long time scales, right? But also, you can do the same thing on very short time scales, right? Same system, right? Very short time scales. Right? How do you do that? Right? You look at physics, the fusion planes for transparency don't exist, right? So it's a different way, and yet you don't have fusion planes in Harry Potter, and other people are making it, right? You're bending it around differently. It's a different construct. And I will not argue that humans don't know how to explain this, but very curious to me that you're doing all this growth, kind of sort of room temperature with water and light. That I find very curious, right? Into the growth cycles, and I find it very curious how energy transfers over the seasons between these systems. And, as I said before, if you know the math, you should be able to go from the outside in, and I think that's always going to have more functionality, or you can go from the inside out. You can go from the not out. So when we graft on something like the property out of argon, we're trying to go from the inside out. And when we're trying to build up brand new property, manufactured properties from the outside in.
Yeah, so one of the things that's really remarkable is like this range of disciplines and discourses that you've done together. I was wondering if you could speak a little bit more about the delivery solutions been and aspects of that we've done these various
Yeah. It's like any new idea, right? You need to have a pretty small group of people that don't think you're crazy, because you have more than opportunity. I've done this for 14 years, right? I've done I have more than one opportunity where I thought I was crazy. Now let's put it in perspective, right? I graduated from the chemical program here, formed my first company, and brought on a very elite set of advisors, right? But it was in chemical engineering, primarily thermodynamics. And I knew the language, and they knew the language, and I could do really good things. And one of the guys is a current co-author, Dudley Herschbach, and I've known him for 20 years. Well, I've known him now for 20 years. But in my first company, I knew him for a little over 10. I started this work in '99. And I thought I had enough data. This is a person I've known for a long time, right? And I think he had high regard for me. It took me 4 years to have enough data where I was convinced I could bring him in and he wouldn't think I was crazy. Not that he wouldn't agree with me. I wasn't expecting that, right? That he wouldn't think I was crazy, right? 4 years, right? And at the same time, I brought in Paul Gray, who's then the chairman, and the same thing, right? And it doesn't mean I wasn't sweating bullets during that meeting. Then we produced our first paper, and the whole key is how do you make it digestible, right? How do you make it digestible for the person in terms of ideas that they can have, track equations they can use, right? The Maxwell equations come down to 4 with the integral forms. They lose all the topology. Everybody uses it because it's easy. The differential equations are the ones that Maxwell used that contain so much more information. They're too hard to use. So you don't do it that way until you get something really simple like a geometric object. So we've had a hard time in the standard peer-reviewed process. The first paper came out, they said it was a discovery paper, they published it, but we submitted it to a journal that said this is impossible. We changed one word. We went from a quasi-element to a sensitized element. And it went through just like that. It went from impossible alchemy to discovery, right? Then we did the second paper where we're shifting this stuff around. They said, you know, this is right, a lot of things are going to have to be rewritten, and you got to get multiple outside confirmation. So we started working on that. But one of the biggest constraints on multiple outside confirmations is they didn't have the instruments that we had available to them. So we were using very, very high energy X-ray equipment, which were tabletop, paid by 18 months to get, $600 US, to something that you could borrow. You could call up group because you're from MIT. You could call up, and they would lend you one for a month for free, right? Which is only $50,000 piece of equipment, but they sell 300 of them, 400 of them a month, right? So, doing a lot of engineering to show different phenomena, it makes it accessible. Then as soon as you get to, wow, this is really real, a guy named General Larry Welsh, 4-star general, and he ran all the material science for the Department of Defense like forever, from 1950 to 1980 or something. And he said, you know, this isn't the gee whiz category, right? Gee whiz because it's really cool, but how do I communicate it to anybody? And that was the first thing Paul Gray said to me. He goes, this is like when computer programming first became hot. We had a guy at MIT who could program anything. He couldn't talk to anybody. He goes, that was a problem, right? So he could put down steps in terms of what is possible, but he couldn't teach anybody how to do it. So now what we've been doing is, because it's all abstract math, now we've been working with a group of mathematicians slowly to get to the people who are in their prime. So I made a presentation last year at the first non-nobel laureate invited to talk at the Nobel Laureate conference at Lindau in 62 years. And the 40-minute conversation went really poorly, and the 2-hour conversation went really good. And it's just a matter of the context, right? If you have something that you have a really difficult discussion you want to have with a friend, you want the right form, you don't want to, okay, I got 2 minutes for this, right? It just takes too long, right? You can't do it. And so in that, I entitled that paper when I gave people the Herod's Court, right? Because you just can't do this. But after you look at all the data, it's like, wow. You know, as one person said, who was stamping up and down saying this is bad science, and I think you're breaking some fundamental laws here. Well, anyways. So, but there is as I was telling Mark, there's an element of social engineering. Because we're having a group come in to evaluate this, which are in the thick of it, and they're in the top of their field. And they are known, they say, given a bad idea to this group is like giving red meat to a hungry lion. Right? So we're going to bring those people in, probably in Q4 this year, Q1. And we're asking them 2 things. We're asking them to vet, to establish whether the experiments are telling us today would be. I think that would be pretty easy. And then the second is going to be, how do you communicate it to your peers? Right? That's much more challenging. But those people are going to want to see data, and then the very first thing you say, right? It's unbelievable. You ever, what's that group? Limbo, right? They first say, if you could do this, I would believe everything. Then you do it. Say, well, you know what? You need to do this, right? And then you do that, and then you need to do this. Right? So as soon as you get to, well, if you could do this, if you could put magnets in copper, first that would be unbelievable. If you could do this in copper, blah, 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 blah. Then it's like, you know, that's the trivial part. The really important part is the math that everybody can understand. So we've begun working with mathematicians to formulate it correctly so that I can speak the right language when I get to the group of young people. Because the young people are the ones that are going to take risks. But if you're not posing the problem to them right, it's too intractable for them. So we're trying to get The more senior people are moving it down until it's well posed.
I'd say you've been here 4 times, and each time the presentation gets clearer and clearer and showing us the fundamental sort of building blocks of the whole thing. And I compliment you because I think you're working very hard at that communication to what is a lay audience. And I guess when you talk to a specialist audience, it's you have to speak with a different side here.
You do, but it's the same thing, because in the 1920, you look at all the top physicists, they were great in a number of areas, and they were really good in all of them. Today, you don't get tenure that way. You get tenure by being like a laser. And so I've spoken to people in some of the advanced departments here. You show them the data, they have no idea what the data means. Or you talk to them about spectroscopy, they don't understand the implications of it. So you end up getting a different group, and then be able to change length scales and be able to change length scales. Because that's been my experience. The kids still really think so.
Thanks. This is fascinating. I'm thinking about a certain relationship here. I wonder if you could say something about it. I mean, I think about special relativity and space-time transformation based on motion within the constraints of light speed and measurement, or the reference frame. And it seems to me like you're doing structural relativistic transformation. And so you're talking all about property changes, but are there also space-time changes with regard to the material, like the copper? Can you measure space-time changes?
I don't know how to measure those, and I can tell you that if I did, I wouldn't tell you. No, and it's because there's 2 things that have happened in the last 4 years, right? One thing that's happened is that we've gotten more data, right? The theory hasn't really changed. Right? The second thing that's happened is I've been more willing to tell people what I actually think. And that took a lot, right? It took a lot as an intellect to, or lack thereof, to have the courage to be willing to say, no, I'm going to go in front of the group, and I don't care whether it's 28 Nobel Laureates, or in physics, or somebody else. And I'm going to tell them what you think. And if you think I'm crazy, too bad, right? And I've studied a lot of the great ideas in mathematics and what percent of those people went insane. And it was a double-digit %. And the same thing in all of them, right? So I'm very cautious on talking about what I think is actually happening when it's happening. But I think that you can look at what the slides are and draw your own conclusions on what has to be happening there.
Do you have to be cautious here?
Oh, because it's being recorded?
Oh, okay.
Oh, no. I got the person with the iPad taking pictures.
But in a way, you're not being cautious. Your papers that you publish have been actually very technical, very constrained in that kind of just anomalous behavior.
Yep.
It's an extremely modest thing, and you're not asking people to and obviously
So we've moved from data only more towards data and theory. And it's I come back, we're all human, right? This object right there is going to change a lot of views in physics. First, because it's one of their gods, right, that have come up with it. So it's one of their own, and they're showing something brand new ways of doing unification, et cetera, space-time is being emergent, all these sorts of things, right? Proof, not speculations like Lawford might have, proof, right? But it's a geometric object, right? It's not a bunch of calculations. So the question becomes, if you can manipulate this stuff geometrically, can you force nature to do the calc for you? That's the key. That's the key, right? And that's why I came back full circle to, I think there's a geometric invariant. So they specify these 2 things. It's the sufficiency condition with the mathematics here means you got all the necessary stuff, and if you do it, it will happen. You know, just be an energy minimum.
What I was trying to allude to in terms of our fumblings in architecture, with moving into a kind of topological definition of architecture, everything relationship, everything around it, new plasticity of mind, if you will, and you're inviting all the experts to manipulate this space with you. It seems to me that is a new conceptual space for design thinking. With this, I mean, when you sense really what's being presented to you, I feel hugely privileged to witness this sort of thinking through the deep logics of matter itself. It's a topological universe. You know, it's like everything, it seems to me, suddenly is topological. So the disparaging of the parametric in architecture is, you know, bad software or something. What I sense for witnessing is actually an emerging paradigm in conceptual thought where everything down to matter itself is topological. And topologically transducible. And what does that do for the concept? I mean, that gets hold of my mind and I can't shake it anymore. I couldn't go back to construction of architecture. And I dying for someone to creatively get hold of it and say, what would it mean by a topological variance of material property? What if you can switch on transparency, flow light, at the speed of light? That's really amazing. Astonishing. Astonishing. One of your little throwaway lines is you put out a few memory ones. I remember you said you hated it after you'd made the putt, that you couldn't change the viscosity of the ball with light at the speed of light. But I will. Yeah, wonderful. Any more questions, Randy?
I really appreciate your presentation. It's very inspiring because I can see you talking about like the fractal from the narrow to the meta structure. Like we also use the fractal to do the urban design, so it's very interesting and also reminds me about the Professor Mark's the response of hypersurface. And I have a question about is this theory only apply to the atom scale or also can apply to a compound or molecular? Because if this could use to the concrete, because nowadays we all use the concrete to build our building, and if this could change to the dynamic instant property, then it can absorb light in the morning or it can emit the light in the night, and it will be very useful. So I can change the property of the concrete or something other natural material. And another one is about.
I think the answer is yes.
Yes, yes.
Yes.
So we
yes,
can.
because it's recursive. It goes. In the beginning, I said appreciating architecture. You ended with a universe, right? I think it really is. I think you can see the same thing all the way over, and that's why in the other one, learning for the master architect, there are trees over here and up here. I think it's the same construct. The key is that right. Mathematically, it's unknown whether we live in a 3+1 space-time or whether we live in a 5-dimensional facility space when we project it. Right? Unknown. Right? So the question is, do we live in 3 space, or do we live in the set of systems that are projected in 3 space? Now, if the beauty of topology is that if you have the ability to change topology, you always can find an answer. Always. And the reason is because you can put in a new hole and that hole can contain an answer. That's the reason, right? The key is, do you know where to look? I said I have a strong view. Where is it? have a strong view on the elements. But once you have an opinion on what these elements are giving you, and you have recursive structures, you start classifying them. And once you're classifying them, bits are primarily empty space, you can start classifying empty space. So what you have here is a pyramid. And they're broken into areas on where I believe property inheritance comes from. And in the beginning I used super, like Superman, and then I realized it really should be symmetric. So a different type of symmetry there. So if you sit right here in natural copper, or in this area, all I have to do is do a traverse and pick up new features. So from a human perspective, I take one of you in the class and I say, I want to give you the talent base of X. Right? If I go back and I change out all these, who your parents were, who your grandparents were, or change the environment depending on the property I'm looking for, I have a high probability of biasing that system. So if I'm going to look for a material that's going to have good superconductivity, I think I could use any element of the periodic table. But there are wiser choices to use and some, and dumber choices to use. It's the same thing here. If I want to put in a particular type of property, these are just numbers, but of course I use the numbers as groups that I pull in when I'm on that traverse. It goes round, and I want to reset my zero. Right? That's what I'm really doing. I'm bringing in a new group to tile out the system. So looking at, to go back, you're looking at your concrete, you're saying, okay, these are the features on it. Now I'm going to come in, I'm going to tweak these particular groups. And those, just like the symphony, they can be, in theory, they can be engineered in ahead of time.
First, we were told that your lecture was going to be the hardest of the year, and it was not. You are very good communicating your ideas, so thank you. And thank you also for trying to make the relation with architecture, because you are the first doing that translation of what you're doing to our field.
A non-trivial effort.
What I wanted to know is what's the next step for you? I mean,
the next,
Very good question.
excellent question. Paul Gray told me, the emeritus chairman, the previous chairman, president, in fact, he said, Chris, if you get it to a level of where you're producing, the academics will have to come. Because if you can't get to that level, then you need them to come. And if you look at what happened with the transistor, that's what happened. The Noyce, Grove, and Intel knew how to do it. And academia didn't. And so all of the best and brightest of academia, still doing postdocs at the sister university, they were all told to go do a job at Intel, and then they'd hire them back, and that would count as a postdoc. So my next step is to get into production on a target that I very well defined. And then it's, you know, I think there's some really cool things here. And Dudley told me, Dudley Herschbach, the co-author, when he drove down for the very first time to see this, he goes, what are you expecting, Chris? I said, I don't know, Dudley. I'm just going to let you see. And when he came back, he said, wow, this looks like the universe reduced down to a crucible of copper. And then the next morning, he called us up very, very early, and he said, wow, I think this is going to unify not just parts of physics, music, art. He had a wide range, because what you're talking about is how things are connected. Right? How things are connected. How do you get ideas? Right? Other than your own? Right? Einstein says you're in the area, you pluck them out. I don't know. Right? But I think it leads to a different paradigm, a different way of thinking. As for me.
So a new unified theory of energy.
You know, I don't want to go on a tape. So is that turned off?
Yeah.
Yeah, right.
Sure.
You asked a question. If you were going to create, if you knew the system was fractal in nature, recursive, and it could be metafractal, meaning it could have branches off with different forms. If you knew that, then you would ask yourself the question, is the current approach to unification going to be helpful? And you might find it's very helpful for one branch. But you might find that what you really need is a traversal. Right? You really need a traversal. If you go onto the web, you know what that means, the traversal? So it's like an onion, right? I don't think there's going to be a final layer. I want to understand how I get through the layers. You go onto the web, there's some very nice graphics on what we know of physics, and it takes you from 10 to the 0 up to 10 to the 34, and then 10 to the 0 down to 10 minus 34. And in some of those minus areas, there's some big gaps on the negative side. And on the positive side, there's a lot that's populated. Well, if it's fractal, there's got to be stuff there. You just haven't looked hard enough yet. So it leads you to a different way of exploring the screen. For me, it's led myself to a different way of exploring the screen in systems.
That's like a great alternative.
For example.
Just like people know. So,
seems to me like there's a nice parallel here with regard to art and architecture, other human scale visual applications of light. Like I haven't thought about it this way, but your talk has activated it. That if we think of this space, right, that we read by the material, what we have learned to be the material layout of things, and then the space that's afforded by that, as a kind of knot itself, right? And the light is really the thing that knots it in the sense of sort of visually reading the space. We can change it by manipulating the material, the material confines, or we can maybe, a parallel to your approach, we can put in new light. We can sort of restructure the light and thereby get a different knot, so to speak, and a different spatial experience.
That's exactly right. I think that that's your knot, right? That's your material, right, as you're saying. And you can impose stuff here and propagate it out, or you can do it and propagate it in. I mean, those are the two paradigms that you're looking at. And everybody has to have a dream, right? And I'm really focused on conservation of material, particularly with human population. And the beauty is we've gotten a lot less materials. We've gone from hardware to software. We still have a massive amount of materials going to dumps. This says I could take a block of copper and have it be the computational capacity of any chip, just by a light sequence, the same one. So instead of updating a new processor for a new operating system, I change in a new light sequence because all the connections are already there. And the people that are pushing quantum mechanics right now, the hardest, are the quantum computation people. They're the ones that are really asking deep questions on what does coherence mean, what does it mean to calculate a number, these sorts of things. And how do you get the efficiencies up in that, rather than just pushing numbers, right? I'm not saying there's anything wrong with that. I mean, it took us a long, long way.
I hadn't thought of it before, but isn't there a new definition of sort of, it's the architecture of everything, the orchestration of everything, but also the, and every one of these groups here probably sees something new. For sure.
That's a great idea.
Thank you.
No, I do. And the same, right? I don't know your name, but I think it's the same. How do you start, I'm not smart enough to do this, and I mean that very, very seriously. How do you start thinking about integrations for better sustainability? Right, because that's where we're headed. Yes, sir.
I really admire your way of telling material and to change the property of material, but is it possible to bring this kind of technology into a more popular way? I mean, I was thinking about the 3D printing revolution. When we're talking about 3D printing revolution today, we're not only talking about creating the shape, also talking about creating the the material and the molecule structure
Mhm.
at the same time. So have you ever think of incorporating your technology with 3D?
I have, and my wife tells me I live under a rock, right? And it's a recursive rock, so I have a very large area that I can explore. But it's a rock, right? So I didn't even know what 3D printing was until July of last year, right? Of this year, July of this year. And I talked to two people. One guy who made a large investment in our company, and the other guy was the head of Department of Defense, blah, blah, blah. And he goes, this is going to have a huge impact on 3D printing for exactly the reasons you're saying. You're now looking at a change in materials, and that's where I go to the geometry, right? You can go A to B, but with things like 3D printing, you're not going from B to A. So you're back to what you can imagine, and how do you bring those sources in, and you start engineering in that utility, because you can. In itself, because it's been made to do that. Right? You've been made to be able to do music, you've been made to speak, all these things you've been made to do. It's just that we've only been using one sensor, so we never knew that.
But I'd say beyond that, beyond variable property sort of 3D printed, it's the potential property that's embedded that can be very real time. So both, and I sense to me what there's some of these kind of changes are permanent and some of them are temporary.
Yes.
And totally together something but it's you're witnessing both.
Yes, and I think the goal, when we had transient properties, I thought, oh my God, kill me, right? But then I realized it was so trivial to disprove contamination, right? And then I spoke to the head of MRI at Brigham and Women's, and said, boy, if you could make carbon magnetic, we could light up a lot of things and see them. We couldn't before. He said, and we don't want anything last very long. We want it to last as long as we can image it, and then it goes benign. But I think the ultimate is a post-it property. 3M taught me that. And I have a little piece of paper on it, I write it down, and I leave it there in the book, and it's going to stay there, hopefully, until I remove it. Right? I think that's what we're looking for in property sets. Because what calculus has taught us is that as I can go to smaller and smaller and smaller differentials, I can get higher and higher and higher performance. So if I want one property, I sort of look at that as a slope on a triangle. If I can get a variety of properties, I look at that as a curve under a differential equation. So now I can move it, just as you said, for different parts of the day or different parts of the life cycle to have the maximum utility at the highest efficiency.
Yeah, I'm curious about intellectual property, just and like how.
I'm sorry?
Intellectual property and like what's the patent process? I mean, what's your opinion on it? I'm obviously you deserve to get paid back for this. There's so much social good. How are you gonna? I mean, is the property like the sequence and frequency of light is a set, and how do you control this? How do you protect this?
Okay, so I'll give you a couple answers to that.
I can try that.
I'll give you a couple answers, right? One answer is my spouse says to me, Chris, we have too much money, and I give it away. And I say, if I give it all away, then I'm not going to have money enough, I couldn't have done this project. Because I invested a lot of my, 50% of my net worth to get into this based on a belief. That's sort of one end of the spectrum. The other end of the spectrum is, if you can do certain things involving water, you have to give it away. Right? Period. You just have to do it for greater social good, and that is my plan. Right? And then someone else says, yeah, but you have minority shareholder suits. And if you give that away, they're going to sue you about it. Right? And so far, the nonprofit organizations are more restricted in the U.S. than in Europe. Right? So when I come down to IP, there's patents and enforceability of patents, right? And then there's know-how and the like. My feeling is, yes, we got a bunch of patents on this stuff, but at the end of the day, the real mechanism is to have broad dissemination. And I don't care whether I have patents or not, the goal is to get the price affordable enough so that it can move forward. And in my opinion, although it's poor, that those people who can afford it should buy it, and those people who can should be gifted. I have an investor that has a bunch of eye clinics in South America. And the wealthy people don't like sitting in the same room as the less wealthy. So he has two entrances to the building. In an entrance one, he charges them X dollars, and it costs them, 1/10 X. And the other side of the building, he charges them 1/10 X. And he says, it works out really well. So I think that between the balance of needing to make money and be a villain, so you can do it, and gifting it away and stealing from your shareholders and doing what's socially good, there's going to be a lot of negative.
Okay, so I guess then, I think that's half the answer, but also just this is like a new type of the information that you're.
It's a new
that's
type.
required to do
So,
it, right?
right. So I've got there's I don't know how many patents are right now. 10 million patents that are issued in the U.S. Right? Of those 10 million, or something like that, of those, there's a very small number of. So in a patent, you have an apparatus patent, right? You have a process patent, and then you have a composition of matter patent. The composition of matter patent is I claim X, and normally it's a diagram, right? I claim that. Then all ways are covered, right? So if you manufacture a new form, let's just say that makes it really easy, right? Water, right? I claim water, right? Now all ways are. So if you make water by combustion, you're infringing. If you make water by preliminary condensation, you're infringing, etc. If you have a process patent, and you claim water by combustion, or you claim water by condensation, and you both get patents. And then in the apparatus, which are normally the weakest, okay, I'm going to make water, I'm going to do it in this vessel with these particular dimensions. I could have these numbers wrong, but I believe they're because of the genetically engineered mouse, there's a reasonable number of composition matter patents, maybe 1,000 or 5,000 or something like that. For inorganic systems, it's like almost none, right? Small numbers. Until about 5 years ago, then it expanded quite a bit. So it's expanded because of us, right? We went through 3 national security reviews to get the first patent, and now we've got, I think, 37 of them, or something like that, can be issued, blah, blah, blah. But what I claimed is this part. So I claimed that this is an integer solution to a particular equation. I just wanted the non-integers. That's what I did. And we got it for all metals, broadly defined. And now I'm going back to try to get the non-metals and the gases in particular. And there's 2 real big reasons you want to do that, which I'll tell you after the movie.
I think we're very privileged to witness this. There's not a lot of group of architects on the planet that have insight into something like this. I think if Bashar's right, then it's a new framing. It can't help but change the way we frame. I would love to see speculative work on this. I think most generally people are too worried by the pragmatics of getting a job. And obviously this is in the horizon. But if anyone's interested in pursuing this, and if thinking through what it might mean for cultural production, for material production, all of it, I'd be very happy to go for action. So it's marvelous.
Thanks. Yeah, I would add one thing on that. Before computer programming, logisticians had no employability. Zero. So first of all, there are a couple of them in academia, no employability. After programming, even hardware, they became the rarest commodity possible, right? If you track how quickly it takes for major innovation to get integrated from the first industrial revolution, second, all the way through, and so look at the time frames, you normalize that by the communication route, you're going to find that if this is true, it takes a while to think about this correctly. And once you do, then it's like, oh, macro. It's a different way of thinking about it. It's curious. Right? So you might find that it gets you a good grade and doesn't really help you out there, and then in 12 months, you might become real important.
Chris, thank you. That's really
Great.
So this next week, please try and come see Martin Jay. He's a very great amateur cultural historian. Terrible if the room was up empty.